Hi. In preparation for this week's lab, we'll be talking about energy and heat. There are some things that don't have mass and volume. Those things fall into a category that we call energy. Energy is anything that has the capacity to do work or to cause change. And although in chemistry we mostly deal with the study of matter, things that have mass, matter is affected by energy. Energy can cause physical or chemical changes within matter. One type of energy that most people are familiar with is calories. Food energy is measured in calories, and if you want to lose weight, you try to run more and burn more calories. You'll notice here I have a table that shows calories of various foods, and over on the right under energy, instead of just calories, it writes this as kilocalories. I'll explain why that is in a few minutes. There are four major types of biomolecules that we talk about: fats, carbohydrates, lipids, and nucleic acids. Of those four, three of them make up our foods. Actually, nucleic acids are in our foods as well, but nucleic acids don't have any calories, and so when we eat foods with nucleic acids, our bodies don't use those nucleic acids for energy. But we do use fats for energy, we use carbohydrates for energy, and we use proteins for energy. Fats have the most calories per gram. Fats or lipids have 9 calories per gram. Proteins and carbohydrates are equal. Both proteins and carbohydrates have 4 calories per gram. Now, if you've ever tried to lose weight, you know that there's a lot more to losing weight than just counting calories. For a long time, scientists thought that because food is just energy and our bodies should be able to just burn energy, and if we can calculate the energy in and the energy out, as long as we have a deficit, we should lose weight. And that is true to an extent, but different types of food really do affect your body in different ways. And if you cut out on some foods as opposed to others, let's say you eat more protein, it's a little bit harder to gain weight on protein. And later on, when we get in towards the end of the semester, you'll understand more about why it's a little bit harder to gain weight with protein. But with any type of food, if you eat too much, you're going to gain some weight. Calories aren't the only way to measure energy. Another unit of energy is the joule, J-O-U-L-E. A joule is a little bit smaller than a calorie, so it takes 4.184 joules to make a calorie. A kilojoule is equivalent to 1,000 joules. Now, I said before that I was going to tell you about kilocalories. Here's the deal. When we deal with calories in science, we're looking at calories with a small c. So science calories are very much smaller than what typical food calories are. When you see a candy bar wrapper and it says it has 250 calories, to a scientist, that's really 250 kilocalories. In fact, if you went to England or Spain or France and you looked at a candy bar wrapper there, the candy bar wrapper would be listed as kilocalories. So just from everyday experience, we have a little bit of idea what a calorie is. But we don't have much experience with joules. So here's a table that tells you a little bit about a joule. If you sleep 1 hour, you're going to spend 10 to the 5th joules. So that would be 100,000 joules. Let me just make sure I got that right. Yes, I did. If you had a serving of pasta or a donut, or if you were bicycling for an hour, that would be equivalent to 10 to the 6th joules, which is 1,000,000. So joules, you can see, are a very, very small unit of energy. When we talk about energy, one type of energy is heat, and we measure heat in either calories or joules. Now, a lot of people think that heat and temperature are the same thing, but they're actually very different. If you think about a match and a bonfire, the match and the bonfire probably burn at the same temperature because wood burns around 230 degrees Celsius. But which one gives off heat? Which one would you want to sit by if you were cold on a chilly fall day? I think you'd choose the bonfire. So what heat really is it's a measure not only of the temperature, but also the mass. And so heat is a quantity that's given off. pretty soon we'll have an equation that will show you how heat and temperature are related. The way that we'll use our heat equation is to look at what happens when a food burns and how can we calculate the number of calories that are given off by that food when it burns. Now, if we were doing this in a food science lab, we'd have something called a bomb calorimeter. We'd put our food in there, we'd add a little bit of an oxidant to make the food burn, and then the machine would measure the amount of calories given off. It would measure the amount of heat given off by the food when it burns. Of course, this isn't the way that all food labels are created. If you have a recipe and you know that you have a cup of flour and a cup of sugar and 3 eggs, all you have to do is look up the calories for each of those individual ingredients and add them together to get the amount of calories in your item that you're creating. So here's the equation that I was telling you about. It relates temperature and mass to heat. The equation is Q equals mc delta T. Q stands for the heat energy. That's going to be measured in calories or joules. M is the mass of the substance in grams. C is something called specific heat, which I'll explain in a moment. And delta T stands for the change in temperature. Now, when you're looking at this symbol here, the delta and the T go together. That triangle is the Greek letter delta. In science, that Greek letter delta means change. Specific heat is the quantity of heat that changes the temperature of 1 gram of a substance by 1 degree Celsius. Substances that have greater specific heats warm up and cool down more slowly than other substances. If you've ever gone swimming on a hot summer day, you jump into the pool and it feels nice and cool, that's because water has a very high specific heat. It takes water a long time to warm up and a long time to cool down. Air, on the other hand, has a low specific heat. So now you go jump in the swimming pool in the evening when the air is quickly cooled down, the water has retained some of the heat from the sun and the water will feel warmer at night. Here's a table of some specific heats of some substances. Notice the units. In this case, they're in joules per gram degree Celsius. That means, for example, for aluminum, it will take 0.897 joules to raise the temperature of 1 gram of aluminum by 1 degree Celsius. Now, if we compare that with copper, it only takes 0.385 joules to raise the temperature of 1 gram of copper by 1 degree Celsius. Oftentimes, pans are made of aluminum with a copper bottom. That, I think, makes sense because the copper bottom, having a lower specific heat, will heat up more quickly and it will cool down more quickly, while the aluminum inside will hold on to the heat better so that it can more evenly cook your food. We don't have a bomb calorimeter in the lab, and I like to do things in a little more hands-on way anyway. So here's what we're going to do. If you notice in the picture, there's a really cool little thing down here with something on it, okay? That happens to be a marshmallow on top of a paper clip. And then you have your Mountain Dew can, and inside the Mountain Dew can, there's some water. Now what we'll do is we'll have measured this water very accurately. We'll light the marshmallow on fire. The marshmallow will heat up the water. We'll be measuring the temperature change of the water, and then the heat that's gained by the water is going to equal the heat given off by the marshmallow. So what we'll do is we'll use our Q equals mc delta T equation. M will be the mass of our water. C is the specific heat of our water. Whoops, my phone just fell down. No big deal, it was the landline. The specific heat of the water. And delta T is the change in temperature of the water. See, we have to measure the heat gained by the water instead of the heat given off by the marshmallow, because we can't really measure any change in temperature of the marshmallow. The marshmallow is burning, it's giving off heat. That heat is going to raise the temperature of the water. So then we'll get this value. After we multiply the mass of the water times its specific heat times its change in temperature, we'll get this value Q. That Q will be in calories or joules, depending on what we choose to use for a value for our specific heat. The specific heat of water is either 4.184 joules per gram degree Celsius, or if we choose to use calories, it's 1 little c calorie per gram degree Celsius. That's kind of cool that the definition of specific heat for water is that it's the amount of calories it takes to raise the temperature of 1 gram of water by 1 degree Celsius. So really a calorie is the amount of heat it takes to raise the mass of 1 gram of water by 1 degree Celsius. Okay, so let's try a simple example. We burn a banana and we have 5,000 grams of water. The temperature of the water goes up from 10 degrees to 30 degrees Celsius. How much heat was given off by the banana? Here's our equation. We're looking for Q. The mass of the water is 5,000 grams. Specific heat of water, which is here, is C, is 1 calorie per gram degree Celsius. And the change in temperature of the water, if it went from 10 to 30, well, that's 20 degrees Celsius. Okay, we can cancel some things here. Let's cancel the grams because we have grams on top here and grams on the bottom of our fraction here. Let's cancel the degrees Celsius here and here. So then we take 5,000 times 1 times 20, which is 4 zeros, 100,000, and my units are little c calories. That's a lot of calories for a banana, but remember, these are science calories. Let's change them to American food calories. To change these to American food calories, what we do is realize that there are 1,000 little c calories in 1 capital C calorie, and then we use that as a conversion factor. So we take our 100,000 calories and using our conversion factor, I want to put the 1,000 calories on the bottom because those are little c calories, so those will cancel, and my 1 capital C calorie on the top. We cancel little c calories, and my final answer, 100,000 divided by 1,000, is 100 food calories. Or if you were in England, you'd say 100 kilocalories because you leave it in kilocalories. Okay, here's another example. You should pause the video right now and try this on your own. I hope you paused it because now it's my turn. 3,000 grams of water is my mass. The change in temperature is 15 degrees Celsius, delta T. Specific heat is 1 calorie per gram degree Celsius. I have everything I need to find Q. 3,000 grams times 1 little c calorie per gram degree Celsius times 15 degrees Celsius. Grams cancel, degrees Celsius cancel. 3,000 times 15 is 45, 3 zeros, 45,000, and those are little c calories right there. Okay, changing it to capital C calories, we take our 45,000 little c calories, and our conversion factor is 1 capital C calorie for every 1,000 little c calories because capital C calories are really kilocalories, and kilo means 1,000. Calories here cancel. 45,000 divided by 1,000 is 45 capital C calories. Now, you might think, well, that's, kind of weird that a peanut would have half the number of calories as a banana because peanuts are so little and bananas are so big. Let's compare the amount of calories per gram for each one on our next slide. So when you burn your peanut and your marshmallow in lab, you're going to have a little something left after it burns. The amount that burned away is the amount of peanut that actually gave the heat. It's the amount of mass that was converted into energy, that was converted into heat energy. So that matter, through a chemical reaction, created heat. So what we're going to do here is we're going to take the amount of calories that the banana had, and the banana, we'll say, had a mass of 55 grams before we burned it. After it burned, some of that mass burned away. We had smoke. When you burn something, it goes into energy and it goes into smoke, and some of the gas vapors go away. So we end up with a smaller mass than what we started with. In this case, we ended up with 30 grams of burnt leftover banana. Well, subtracting those shows me that I had 25.0, if I use sig figs, 25 grams of banana that burned, 25 grams that were used to create the heat. So if I want to find my calories per gram, per always means divide when we do math problems, I take my 100 calories from right here, and I divide it by my 25 grams that burned, and I get 4 calories per gram. Now let's take a look at our peanut. Our peanut had 45 calories, had a mass of 6 grams before it burned, and then there's just a little bit of residue left. There was 1 gram left of residue. So 6 minus 1 gives me 5 grams that burned away, and that's what created the heat. So we'll take our 45 calories, divide it by our 5 grams, and we get 9 calories per gram. So bananas have a lot of carbohydrates in them. You might recall from the previous slide that carbohydrates have 4 calories per gram. Peanuts have a lot of fat content. If you look at a peanut label, you'll see that there's quite a bit of fat in peanuts. And that's really why they burn so well. It's kind of fun in lab to see how well they burn. So peanuts have 9 calories per gram because that was the amount of calories per gram of fat. Now, when we do this in lab, you're not going to get perfect results like I did. I just made up numbers and made them work out to be perfect. But you should find that your peanut does have more calories per gram than your banana. So thanks for listening. I hope you have a good day.